I'm going to be talking about a project called Hydro today, which is an umbrella project that comprises a bunch of work we've been doing for the last 3 or 4 years that's really focused on how we're thinking about the future of programming the cloud and taking advantage of cloud infrastructure. And our first cut at this has been thinking about how to bring state management into the serverless computing world as a first-class citizen. Just as a brief bit of background, I want to tell you a little bit about why we're so excited about serverless. From our perspective, the most exciting thing about serverless is that it enables programmers to take advantage of resources in the cloud that wasn't really possible before. It was true for folks who worked at Amazon and Google because they've been building these cloud scale systems for 15 years now. But for everyone else, we were still using the abstractions that existed when we were building applications that ran on tens or hundreds of machines, not thousands of machines. So serverless provides a bunch of new opportunities, the first of which is access to a scale that wasn't really possible before, thousands of cores and petabytes of RAM that I can actually get on AWS Lambda or Google Cloud Functions today with the click of a button. I can write a function, I can upload it, and I can parallelize it almost instantaneously without doing any of the hard work of waiting for machines to spin up and making sure that they're all configured correctly and they have the right permissions. All of that stuff is just done for me. The second thing that we're excited about is fine-grained resource usage and efficiency. That's something that's been a sort of promise of the cloud for more than a decade now. When we wrote the Berkeley View on Cloud Computing 10 years ago, increased utilization was one of the predictions that was put forth in that paper. And that never really totally came true in the VM-based world because everyone just ended up allocating all the VMs they needed, and then those were idle when they weren't being used, and we sort of reverted back to how things were done before. But serverless actually allows you to get resources exactly for the time that you're using them. You pay only for what you use, and those resources can be repurposed for some other customer when you're not using them. So we can actually get this very fine-grained resource usage. And the last thing, which I'll come back to towards the end of the talk, is enabling new economics and pricing models. So really starting to think about how we price compute, how we price memory, how we price storage, how you can get consistent performance compared to what exists today, and what the pricing and economics of all of that looks like is a really exciting research direction. So that's the rosy side, but what exists today has some serious limitations. We've all heard of these. These are things like limited runtimes. Your functions can only run for 15 minutes. You can't use any heterogeneous hardware. You have to use just CPUs. And some more fundamental things, some less fundamental things like the fact that all of the I/O that you do in your applications has to go to a far away and generally very high latency storage service. Or the fact that you can't open sockets and communicate between functions, meaning that you can't do any sort of direct communication. You have to again go through all of your high latency storage services. So the implications of that are that what exists today has the fast systems have serious data and communication problems. They force you to do data shipping, and they force you to go to a slow storage service. So the first project I'm going to talk about today tries to solve this last problem of having a high latency autoscaling storage service. There's obviously systems like Redis, which we all know are very fast, but they don't autoscale. Even the cloud deployments are fixed deployments. And in a serverless setting, that can become a bottleneck really fast. So what we set out to do was to build a key value store that looked like S3 in that it automatically scaled up and scaled down to match the volume of the data and the workload that you're throwing at it without having user intervention to spin up more nodes or to move data into memory or whatever it is. But gave you the performance characteristics of a system like Redis where you get memory speed performance a large majority of the time. It's called Anna. We've been working on this for a while. This is the most mature component in our stack. So the goal here is to build a KVS that performs like Redis and looks like S3. One of the key insights here is that providing very strong consistency guarantees, things like serializability or linearizability in an autoscaling setting is actually really hard because all of those guarantees at the end of the day require that you know all of the machines that are responsible for a certain piece of data in the cluster. That requires coordination, and coordination can be really slow for those kinds of protocols. In an autoscaling system, you're going to be changing membership pretty often. You're going to add machines, remove machines, repurpose them, repartition your data, do all sorts of things. And given that high flux, if you had to run this expensive coordination protocol every time, that's going to significantly inhibit performance. So one of the core design principles in Anna was to avoid those kinds of protocols, and instead to use these coordination-free consistency protocols that we developed to basically allow us to get decent consistency. You're not going to get linearizability or serializability, but we can still make meaningful consistency guarantees while also providing really, really fast performance and very, very flexible auto-scaling infrastructure under the hood. The way that we do this is by using these things called lattices, which are these data structures that allow you to accept conflicting updates in parallel and then resolve them asynchronously. I don't have time to go into detail, but I'm happy to talk about those later if anyone's interested. So on top of this very fast storage kernel, we adapted the system to run on a bunch of different storage media. To start with, we did memory and disk for cost efficiency. And then we tied the whole thing together by building an auto-scaling and monitoring engine that monitors workloads and automatically scales the system up and down, but also replicates data on a very fine-grained scale to make sure that hot data has more resources allocated to it, and will automatically move data from disk into memory. So you get, again, some of these nice S3-like characteristics where you don't have to manage these things. You don't have to say, hey, cache this piece of data. We'll detect all of that for you, but the performance, especially when you're hitting the memory tier, is comparable to a system like Redis. So just to brag a little bit about the performance of the system, this table shows utilization relative to other state-of-the-art memory speed systems. And what we're able to show is that using those coordination-free techniques I mentioned, we're able to get about 90% of the cycles of the system are spent handling user requests. Mastery, which is a research system that is that's a state-of-the-art key-value store, uses lock-free atomic instructions. And those lock-free atomics basically spend a large portion of the system's time blocking on each other, and so you end up with less than 10% utilization. In terms of actual systems metrics, that means that for a contended workload, which is the graph on the bottom here, we're able to achieve almost an order of magnitude more throughput than Mastery in a system like Redis, because they end up contending on the same pieces of data where we're able to accept updates in parallel and resolve those updates later. Okay. So coming back to the serverless story, we have this fast key value store, so you're probably thinking, great, we've solved the S3 problem, we have something that looks like S3 and is fast, let's just drop a fast platform on top of it, and then all of our state management and serverless will be solved. It solves some of the problems, but it doesn't quite go all the way. In particular, a core challenge here is that there's still a network bottleneck that sits in between where your compute is living and where your storage is living. This is commonly referred to, if you talk to folks who work on serverless, as disaggregation of storage and compute. And that's a really neat idea because I can now scale up my storage resources and my compute resources totally separately. And if I have applications that need more of one and not of the other, I don't have to couple them like you do in a VM-based world. But the problem is that the network is still a bottleneck in most of this infrastructure. So you're paying a very high network cost to move data over the network if you're doing data-intensive operations. So we did what any good computer scientist would do, and we added a caching layer that sat in between the fast platform and the key value store. This is a project called Droplet that we've been working on for the last year or so. There's a paper that's currently under submission, so we can't share it publicly, but we're always happy to chat in person. So caches improve performance. We all know this. This shouldn't be groundbreaking for anyone. And I'll come back to this in a second, but we're able to actually significantly outperform systems like AWS Lambda for some data-intensive tasks. But the drawback of that is that caches introduce these new consistency challenges. Fast applications are never going to be single functions. They're always going to have a bunch of functions, and those functions are going to run on different machines or in different places based on whatever the scheduling and resource requirements that they have are. What that means is that we now have to worry about providing a consistent view of the world across multiple physical clients. I can be running, if I have K functions, they might run on K different machines, but they can't just read arbitrary data because the application would go haywire. You need to make sure that you're providing a consistent view of the world. And it helps with some of these challenges. The consistency mechanisms I was talking about a few minutes ago take a step in this direction for single keys or if all your functions are located at a single client. But obviously for reasons of fault tolerance and load balancing and scheduling and so on, you're not going to run your whole application on a single machine. That would be silly. So what we've done in the Droplet project is develop some new consistency protocols for distributed client sessions. A single logical request can move across many different physical machines over time, and we're able to provide a consistent view of the world to that request. In particular, the kinds of consistency that we provide are repeatable read. So if an earlier function reads a particular value of a key, a later function will always be guaranteed to read that same value. And something called causal consistency, which is a stronger guarantee that basically says that you will never read older versions of data that influence the data that you read. In terms of performance, like I said, this is a micro benchmark that tracks the end-to-end latency of a task that takes a very large input, anywhere from 80K to 80 meg, and runs a very simple function on it. In this case, we're just summing the elements of a large array. And what we're able to show is that avoiding these super expensive data fetches that go over the network allow us to outperform AWS Lambda over Redis and over S3 by up to 3 orders of magnitude, because we're avoiding data transfer costs and we're avoiding deserialization costs, which end up being really, really big bottlenecks in these systems. In terms of real-world applications, we implemented a Twitter clone on top of our system, and this is a case where consistency actually really matters. You can imagine that if you're scrolling through your Twitter timeline, it would be kind of weird if you saw the response to a tweet before you saw the tweet that it was responding to. And that's actually a guarantee that causal consistency avoids, so it was a really natural fit. And the system basically imposes no overheads for reads when running with causal consistency enabled, and imposes a small overhead for writes, but is able to scale much further than Redis, which doesn't give you any consistency guarantees once you start sharding your data. So that's really neat. And then the last application is a prediction serving pipeline. We took a simple MobileNet implementation and we ran a 3-stage pipeline that pre-processed the data, ran the model, and then post-processed the results. And we compared our system to a local Python implementation, as well as Lambda and SageMaker, which is a purpose-built system that does model prediction pipelines. And our system is about 10% slower than the local Python implementation and outperforms all of the other implementations by anywhere from 50% to 5x. So really real world sort of topical task, and we're really excited that we can get some pretty impressive performance on that. Sorry, what was that? Can I define stateful? So what we really mean by stateful here is data-oriented, right? Stateful sort of, it's a vague word, but we are basically focused on making tasks that have large amounts of data involved in them much more performant. That's the sort of goal here for fast applications. Okay, so that's a sort of whirlwind overview of what we've been working on so far. What I want to do for the rest of the talk is spend a little bit of time telling you about the future directions that we're going in that we're really excited about and are looking for folks who are interested in collaborating on. The first one is data science and sort of edge versus cloud computing. There's a couple projects here, but one that we're really excited about is implementing a serverless version of the Jupyter project. We're working with the Jupyter team on campus, and Fernando Perez is faculty in the stats department here. And what we're taking sort of there's two interesting parts of this project. The first one is a resource consolidation aspect, where the standard deployment for Jupyter is basically we allocate a VM on campus course infrastructure, for example. We allocate a VM to a student. That VM runs for the whole semester. Those resources are allocated. Whenever the student does their homework, that VM will always be running. But obviously that VM is idle for most of the time. So we want to consolidate those resources and make sure that we can get higher utilization by multiplexing many students onto the same machines when resources are idle. More interestingly, sort of as we move past that first step, we're really interested in thinking about how we can be smarter about where computation runs and when it runs. You can imagine that if you're doing a really small computation, like an operation over a 100-row data frame, it would be pretty silly to spin up a whole Lambda, ship your context to the cloud, and then run it there. So what you want to do is run that locally. But when you're doing a much larger operation, you probably want to pay that cost so you can get more resources, more parallelism, whatever it is. And if you need very fine-grained parallelism, serverless can do that too. Because what you can do is you can say, I'm going to run a hyperparameter tuning optimization or operation here. I want 1,000 cores for the next 10 minutes to run in parallel to do all my hyperparameter searches, and then I'm going to make them all go away. And that fits the mold of serverless really nicely. So thinking about these further systems optimizations that can make us smarter about how we use our resources and where we schedule things to run is really exciting. The next thing that we've been thinking about is cloud-native programming models. This is a topic that students in Joe's group have been working on for more than 10 years now. But the core idea here, which I already alluded to, is that the abstractions that we have for programming the cloud today are still very server-oriented and still focused on allocating resources in a very coarse-grained way. And serverless is exciting because we're starting to move away from that. We're moving towards finer-grained resource allocation and more flexible deployment models. A thing that's probably going to need to come along with that is programming abstractions that fit that model. We're interested in thinking about actors as a service and how you can get really fine-grained auto-scaling and fault-tolerant actors to fit in the serverless mold, but also starting to think about streaming and other data-oriented programming models that will allow us to get high performance, but also take advantage of the scale of the cloud in a way that's pretty difficult with today's programming abstractions. Okay, so the next thing is fault tolerance and isolation. This is actually what I'm working on right now, so I'm really excited about it. Serverless has this really nice aspect of simplicity to it. You run functions, you don't have to worry about where they run, when they run, and all those things are taken care of for you. But if we come back to this idea of serverless applications having many functions that run probably in different places, or at least on different physical machines, fault tolerance actually really quickly becomes a challenge. Because what you're going to run into is function 1 is going to run somewhere, it's going to write some updates to DynamoDB or to S3, and then function 2 is going to run and the request is going to fail. And maybe you're going to retry it. But now the burden is on the programmer to make sure that either their code is all idempotent, and as much as we all like talking about idempotent code, it rarely actually is, or they have to actually manually write undo and fault recovery protocols that traditionally have been taken care of by the underlying relational database, but all of that is being surfaced to the programmer now because there's no other way to deal with that. So we're thinking about how we can bring fault tolerance, at least for one particular kind of operation, which in our case is updates that are made to a storage engine from a fast layer, transparently to the user, and make sure that they're able to write their programs as if the underlying infrastructure was totally fault tolerant, and they don't have to worry about doing these undos and redos and worrying about dirty data polluting their storage engine without having actually committed. Okay, so the last thing is autoscaling and scheduling policies. All of the policy engines that sit in Anna and Droplet are pretty heuristic-based right now. And as our friends at Amazon and Google like to remind us every so often, that really doesn't work in production. All of these heuristic-based policies tend to be fairly susceptible to adversarial workloads and tend to go into hysteresis if you find the right way to make them go crazy. So there's a lot of interesting work to be done here around how you can make policies for autoscaling and scheduling tasks on these systems much more efficient. Luckily for us, there's a pretty big effort in the lab already that's been thinking about how to do autoscaling for machine learning model prediction pipelines. And so we're interested in taking that work and trying to see how it applies on a more general scale to more general purpose compute rather than focusing on a particular task. Okay, so the last part that sort of overarches and ties all of this together is pricing and marketplaces and thinking about the economic models, like I mentioned earlier, that tie all of these things together. So we're interested in not just providing the systems infrastructure that runs all of these applications, but also thinking about how both the providers and users should be thinking about the economics of all of these things. An interesting question that I mentioned earlier is how you should think about pricing memory. If we actually disaggregate memory from compute, which is not true in AWS Lambda today, by the way, or the other serverless offerings, we can now say, I can price memory residency. I can tell you that across your requests, I will make sure that certain data stays in memory for a certain amount of time. And then we can start thinking about how we actually make that truly serverless. You don't need to tell me how long something should stay in memory. I'm going to automatically make sure that things stay in memory with some caching policy for the quote-unquote right or optimal amount of time. That sort of dovetails with this whole other idea of providing consistent performance for all of this infrastructure. What exists today is pretty high latency and highly variable. But as we start innovating on the systems infrastructure that makes this stuff more performant, we also want to think about what the SLAs that come along with these things are. Can we actually give you a contract that says 90% of your requests will run in under 100 milliseconds, for example? What is the feasibility of that from a systems perspective, but also what are the economics of that? This is a really interesting and really broad direction that we're really excited about. And if anyone has thoughts or is interested in collaborating, we'd love to hear from you. Okay, So that is my whirlwind overview of the project. There's a lot of stuff that I talked about, and this encompasses a ton of different people's work, and I probably didn't do most of it much justice. A lot of the people who work on this project, they're all wonderful people, are in the room and would be happy to talk to you. All of our code is also open source, so if you're interested in Anna or Droplet, you can find those on GitHub over there. And if you're interested in any of the very many things that I mentioned, we would love to collaborate and chat, so please reach out if you're interested. Thank you. Yeah. So when you say reliability, sorry, the question was, are we? Mm-hmm. Right. Yep. Yeah, so the question was how we're thinking about reliability in terms of performance. For example, when you ask for a new VM, if you have to wait a long time for it, that affects your scheduling problem. There are a couple answers. One is that technology is already getting better. We see with things like Firecracker and gvisor that we're able to get very strong systems isolation guarantees while getting relatively small spin-up times compared to what a traditional hypervisor provides. The other answer is that some of these things are somewhat fundamental constraints, and we're trying to take them into account when we're developing these policies. I'm not an expert on those policies, but Joey would probably be happy to talk more about those things. But from what I understand, those spin-up times and the costs that are sort of the physics of the system, so to speak, are things that we have to take into account to be able to provide reasonable guarantees. And if that means we have to wait 5 minutes, that means we're going to have to be more aggressive with spinning up VMs in advance to make sure that we have resources on hand when we need them. Do you want to add more, Joey? Okay. Yeah. We are interested in thinking about how to incorporate it with Ray, in particular thinking about especially the Ray front end as a really natural way of doing serverless tasks and seeing how that can dovetail nicely with some of the systems infrastructure, especially the data-oriented infrastructure that we've built. We are unfortunately understaffed, so we don't have anyone working on that at the moment, but it's something that we're really interested in. Yes, so the smart caching layer is basically just the combination of the caching performance improvements that I was talking about, plus the consistency protocols. I didn't go into too much detail on those, but the idea is sort of that we have caches that live on each physical machine that's a worker in the fast system, and those caches are able to communicate with each other to provide this notion of distributed client session consistency. Huh? Do I directly what? Yes, that's right. Directly from cache to cache. Yeah. So the question is, what is the atomic unit of a function? Right now, it's all Python functions. So we execute Python functions. That's not fundamental. We just picked it because people write Python. We are thinking about other programming models, and in particular, both what the language constraints are, but also what the sort of deployment model would be, and that will probably change from language to language depending on what the abstractions are. All right, cool. Thank you, guys.